Hello all. It is wonderful to be back at the Flash Memory Summit, talking to you all about the advancements in semiconductors, in flash technologies, and in data architectures. People have been talking a lot about the profusion of data, the amount of data that is flowing in from the edges, from the endpoints, up into the cloud. The big battleground that is in front of us is how do we get the maximum value out of this data? We at Western Digital are particular that we give you an ability, an infrastructure to store and access the data in a secure fashion. We're going to be talking to several key Western Digital executives on what they are doing with respect to this ability to take the data, curate the data, and be able to deliver it in a fashion that you can get the maximum value out of this data. Conventional thinking is that compute dominates the data architecture. We've been seeing this over time as Moore's law slows down in both compute and in DRAM. Purpose-built architectures are showing up everywhere. Purpose-built for different workloads, whether it is for search, whether it is for video, whether it is for database acceleration. Many such workloads require additional specific semiconductor solutions in the compute space. That's because overall, you can increase the number of cores, but you are not able to shrink the transistor much further rapidly. Similarly, in DRAM, the density of DRAM is not growing up. But there is one place where Moore's law is alive, well, and kicking, where we have not hit the Moore's wall, and that's in flash. In flash, that's happening because we have these two new additional ways of scaling. We are not just scaling in one direction. We are not just scaling in the Y direction. We are also scaling in the Z direction. X, Y, and Z scaling allows for rapid scaling of flash, as we saw with the 3D NAND revolution that happened in the earlier part of this decade. What goes in association with that is logical scaling. The ability to get from 2 to 3 to 4, now we are talking about 5 bits per cell from that same die. That allows for this rapid scaling of flash. We have to keep in mind that this amount of data is useful if it is stored. Stored literally means at the end of it, a bit has to flip somewhere. We at Western Digital feel morally responsible for being able to provide you with that ability to store and secure and access that data. So when we have X, Y, and Z scaling and Moore's law continues to work for 3D NAND, and we are able to provide you with this 256 gigabit, 512 gigabit, 1 terabit, 2 terabit die, and we are able to provide systems, solid state drives, small die for edge applications, large die for cloud applications. These are happening. What happens next? What happens when these are put into systems? What is needed to make this data be accessible? For instance, how do we marry an operating system to the characteristics of the media, what we call zone named storages, ZNS? What happens when we can build controllers with open source architectures such as RISC-V? What are these controllers going to be able to provide in terms of ECC or in terms of the front and back end host controllers? What can we do with security? We know that security threats against data are proliferating. What do we need to have a root of trust established around the flash? What does it take to network the storage? What does it take to put it in an NVMe over fabrics? What does it take to make sure that there is accelerators, the AI accelerators that can seamlessly sit on that same fabric so that we can now, instead of moving all the data back and forth to the processor, can now do it in the appliance itself. where some command from the host makes sure that the data and its processing happens in the storage appliance. What happens with video? Smart edge video sensors to make sure that we do local inferences. How do we make sure that edge intelligence makes this happen? All of these and many more such as these are important developments in and around the core strength of storage. Western Digital revolutionizes and takes the core storage strength and then applies to all of these additional applications that go around the data. We are going to be talking to several experts today on each of these applications. I'm looking forward to these conversations. Let me introduce to you Dr. Yan Li. She is the Vice President of Silicon Technology and Manufacturing. She has over 200 patents and is a distinguished member of the IEEE. Yan, you and I have worked together now for the better part of a decade. 3D NAND and its scaling have been pushing Moore's law further and further along. What are the new things that are happening in Flash that are keeping it scaling so very well?
So 3D NAND indeed scaling very well. We have two aspects of scaling, physical scaling as well as logical scaling. Let me talk about the physical scaling first. The physical scaling, we are very good position avoid the lithography limitation. So we build the 3D NAND so that can continue scale according to Moore's law. And we're not only growing the layers from 48 layer to above 100 layer in production now. We're going to go to 200 layers pretty soon. We're also going to shrink the XY dimension to packing more memory cells in each layer. So this actually multiply the scaling effect. Not only that, we're also hiding the peripheral circuits underneath and above the array to get the full benefit of scaling. On the logical scaling side, we have the TLC, 3D TLC 3 bits per cell, is already replacing the 2D NAND MLC completely in lots of product. This is because the 3D NAND is a very good cell, very big cell. And then now we are going for QLC, the 4 bits per cell. The 4 bits per cell will go to mainstream SSD pretty soon because the 4-plane architecture we are having starting in Big 6 generation. So people already work on the 5 bits per cell. We have PTL called. And we have a system side architecture-wise zone namespace, so-called, and also helping out the QLC into production into lots of SSD product. With all that, our scaling basically propel all these large capacity in the small footprint is a very good scaling path.
Now, we think of storage as a static thing. We think of it as a fixed, hey, this is what a block storage device is going to be. But you now are making it very dynamic. What's happening with this level of active dynamic scaling and active dynamic characteristics of 3D NAND?
So the key is we have wide applications from edge device to all the way to data center. For example, the edge device need a low power, high performance, but data center need a high capacity and a high endurance. So we have a very wide applications. We designed one NAND chip, but we designed so many different variations to trade off power, energy, endurance to get there. So, we scaling the I/O speed. Our I/O speed goes from 400 megabyte to 2 gigabyte, fivefold in 4 generations. So all these innovation actually propels, drive the innovation in the NAND. NAND is never static. Is everything have lots of things going on every year.
I also learned from you more and more that we are adding a lot more intelligence to the NAND device. What do you mean by that? I mean, I thought it was just read and write and erase. That's all we used to do with the NAND device. What's this intelligence doing?
So, the big data grows by the second dramatically. Every second we generate so much data. the data analysis suffers from the conventional von Neumann computer architecture nowadays. The conventional architecture basically bring all the data from storage and move to the central location of a CPU, GPU get processed. But this moving takes lots of energy and latency, takes time. So this is something we have to break for the big data problem. Big data require a new solution. So we want to move the compute as close to the storage as possible, even inside the NAND. So as we scaling the NAND, we also improve the CMOS. There is a potential in the future we actually build the intelligence inside the NAND. So NAND not only can store the data, we can also compute, encrypt for security, and ECC for data integrity, even adding AI functions. So this could be a game changer in the future and completely changing the architecture and the functionality of the NAND.
So you're telling me this simple block device, the flash memory, is scaling on X, Y, Z, and logic. It is very dynamic in that you are designing for the edge, you are designing for the core with characteristics of high endurance or low power, while at the same time figuring out how to add more logic, more intelligence into the CMOS circuitry under or above.
Absolutely. We can do that in the future.
Thank you.
Thank you.
It's my pleasure to introduce to you Dr. Richard New. He's the Vice President of Research at Western Digital. He was one of the inventors of the shingled magnetic recording architecture and now on to ZNS, the zone namespace architecture. Richard, we've been talking about computational storage, the idea of bringing compute ever closer to storage. What's new in the field of computational storage? What is exciting about it? Why should we care about it?
Thanks, Siva. So that's a great question. So I think it's probably fair to say that one of the significant trends in compute during the last decade has been this idea of moving compute from a central processing unit out to some other device that can do the compute more efficiently. So, for example, think back to a graphics accelerator card, later GPU, accelerating machine learning functions, other types of inference on machine learning accelerators. So these are, or DPUs, these are all ideas of, you have a specific kind of compute that instead of doing it on a CPU, you can do it more effectively in a custom architecture. So computational storage extends that idea. And the idea there is to take compute function that would be in the CPU and move it down to the storage device. And if you think about it a little bit, you can figure out what kinds of applications or compute functions might make sense in that context. So if you think about, for example, a box of SSDs connected to other servers through a network, you can imagine that the aggregate bandwidth of all of the NAND die on all of the SSDs is much greater than the network connection. And so you could propose, for example, that there might be some compute functions that you could do that require very high throughput to the storage device, and maybe not that complex a compute function that you could execute on that platform very effectively. So a classic example would be a pattern match function. So if you want to scan through all the data just looking for a particular pattern, that's something that is computationally very easy but requires very high throughput to the storage device. So that would be sort of a candidate application. Maybe for databases you would think of row filtering or column filtering. So these are all ideas that potentially have application in the computational storage space. The other aspect of these types of computation, it's really good if you can, for a pattern match function, if the amount of data that you need to return back to the server is much less than the amount of data that you would need to scan. So if you're trying to find a particular pattern in a large pool of data, you can scan through and you only have to return the match locations, for example. So this gives you some idea of the types of compute functions. I call them like the basic compute elements or primitives that you could use for computational storage. And then the problem is to find a larger, more general purpose application, let's say a database. You want to find an application where a significant amount of the compute, let's say in a general purpose query, is really executing these primitives.
This appears to be as big a software problem as it is a hardware accelerator. What is Western Digital doing about the software ecosystem that needs to go with this?
We have a significant investment in Linux, open source software in general, and Linux kernel in particular. And one of the things that we have learned is if you want to work on storage architecture, you need to have, a minimum, a very good understanding of how things work on the host software side. And, I think back to earlier in my career, one of the eye-openers for me, I remember, this is way back on hard disk drives, we wanted to change the block size from 512 bytes to 4 kilobytes. And of course, this was a no-brainer. If you were a hard disk drive guy, you make the ECC more efficient, you gain, 10% or more areal density very, very easily. But of course, it took a decade or more, probably more than a decade, to get that accomplished in the industry. And some people would probably say it's still not done. So this gives you some idea that, if you want to innovate on the storage architecture side, you need to be able to innovate also on the host software side. And so more recently, you mentioned zone storage. So we've applied that principle there. So zone storage is an umbrella architecture, or like a common architecture for SSDs and HDDs. On the HDD side, it's for shingled magnetic recording, or SMR HDDs. On the SSD side, it's for zoned namespace SSDs, or ZNS SSDs. And those two types of media share a common set of constraints. When you write to these media, you want to write sequentially within a zone. So we have worked recently, and I believe led the industry in terms of defining this zone storage architecture, and also creating the software ecosystem to support that. And since you mentioned computational storage earlier, computational storage will be even more like that. It's even more of a problem where the problem statement itself really comes from the application side. It's easy to make a device that performs a specific hardware function, but you really have to be able to support that in the software. So that's a tremendous area of focus for us.
I'm going to switch topics on you. Another important area in storage is security. How does Western Digital think about security? What are we doing about it?
One thing we can say about security is that any data storage company today, or any data processing company, whether they like it or not, they're a security company. So I think that's commonly understood in the industry. And as far as security itself is concerned, let me focus on two different domains. One domain is the area of, I'll call it security building blocks. So we're talking about cryptographic algorithms, security protocols, the sort of industry accepted procedures and policies for certification, et cetera. So in this area, these security building blocks, our general view is that, this is an area where you don't get a lot of points for style, or innovation, really. I mean, it's not, there's a place for innovation, but if you innovate the next cryptographic algorithm, it takes, 10 years for the industry to vet it. So when you're talking about making a security product, the strategy there is to use these tried and true cryptographic algorithms and policies and procedures and protocols, et cetera. And our belief in that space is that the industry will move to open and inspectable architectures. So this will take a while, but this is one of the reasons why we were co-founders of the Open Titan project, along with Google and Low Risk and Nuvoton and G&D and others. And the idea here is that the most secure solutions will be built around open and inspectable architectures, where people can go in and examine the implementation and find problems, et cetera. And it's through that open vetting process that you end up with the best solutions. So in the space of these security building blocks, that's the way we think the industry is going to head, towards these open architectures. There's another area of security, of course, which is taking these building blocks and making something for your customer, providing a feature or a service. And of course, in that space, there's a lot more room for innovation. And so I think fundamentally the message for security is that the differentiator, if you like, in security space is really more about the company culture. How you think about security. Do you take it seriously? Is it a burden? How do you handle that within your company? So it's a matter of having the correct culture within the company, and also supported by policies and procedures to really create a strong security environment. So that's the way that we think about it.
Thank you, Richard. Appreciate it. I have the pleasure of talking with Ihab Hamadi. Ihab is a fellow of Western Digital. Ihab's past experience has been across the board in the semiconductor space, whether it is in networking, whether it is in compute or storage. So let me take that question from there. Ihab, we have been proudly talking about the fact that we continue to scale in storage, but it is not quite as fast a scaling in both compute and in networking. What's the implications to overall architectures? What is this leading to in the industry?
Yeah, it's interesting, Siva. It's been a fascinating journey with Moore's Law, with the semiconductor industry at large. As we look at the CPU within a server today, the single thread performance has been mostly stagnant for the past number of years, while everything around it has either been getting larger, as in the case of storage of all kinds, getting faster, as in the case of networks, getting even more responsive, as in the case of lower latency interconnects, lower latency flash, and so on and so forth. And moreover, the amount of data that the world continues to generate is continuing to go up. The problems that we're trying to solve continues to actually go up in complexity, and the type of insights that we're trying to extract also continue to go up in complexity. So the question is, how do we drive the performance needed to get us to the next level of requirements that are presenting themselves? Within the data center specifically, there are broadly 3 different areas that will help us get to the level of performance, or actually drive performance through the next decades. And the 3 areas are, 1, distributed compute being embraced broadly in all of its forms. And this is an exciting area. It has been around for a long time for things like HPC, but now it's making its way through the data center, to the edge, the micro edge, and all the way to the end user devices. Computational storage is a very interesting technology that is really at the heart of it. It's a form of distributed compute. The second area is really the ability for us to match the workloads, the various workloads of today, with a suitable set of infrastructure. And this is where things like composable disaggregated infrastructure or composable infrastructure come in. The third area really is our ability to drive better performing applications and removing inefficiencies across the stack, really, on the server. So whether this is starting with operating systems, kernels, drivers, libraries, all the way to the applications. If you take SSDs, for example, they present traditionally a well-abstracted and familiar block interface. And this block interface is great for end-user computing, laptops, even personal workstations, and so on. But as you get into the data center, the scale really starts to matter a lot. And all these inefficiencies begin to really add up. So the ability for us to remove duplications and reduce inefficiencies begin to yield improvements around things like durability, things like better endurance, and things like even higher performance that's consistent whether you're doing reads and writes, for example, at the same time. So zone storage, for example, is one technology we're very excited about that delivers all of these advancements. And we're excited to be announcing a new data center class drive that is compatible with ZNS, which is now all part of NVMe. It's all open standards.
Very, very interesting. Now, you also mentioned going from the core cloud to the edge to the endpoint to the end user devices. Data architectures across this spectrum. What's new? What's happening from the core to the edge?
It's very interesting the amount of change that the industry at large is going through, Siva. Let's take video gaming as an example. And it's a very exciting time for gaming, especially as we look at things like cloud-hosted games. Today, you can instantly gain access to the latest titles in cloud gaming from your mobile device. So now if we look at what's really enabling this experience, starting with the data center core, what you really see over there is a collection of console boards. In some cases, there are all within what looks like a specialty server. It could be a 2U server housing as many as 8 of these consoles. And right above that, you will see a set of switches that are providing virtualization capabilities. Right on top of that, you'll see VMs or containers that are talking to these switches that are actually also connected to cloud storage, and this is where all the games are stored. We're seeing that being mostly flash due to performance reasons and scalability reasons and so on. Along with that, you also see control plane functionality there with the ability to spin things up and down to match the workloads and to match the needs of the specific games that you're playing. So what we're seeing there in terms of requirements for storage is more NVMe, again, due to its mostly performance reasons. We're seeing a lot of advanced telemetry that enables continuous tuning for the storage. We're seeing a variety of form factors from U.2 to E1.S, E1.L, and so on. And as we make our way out to the edge, and this is where, as a gamer, this is the first point of connection that you'll get. The first thing that you see is a CDN, or a content delivery network, and this is where you get a lot of the data cached. Specifically the static data and the data that doesn't require rendering, for example, and so on. This is a great area for some of the higher density flash like QLC, and in the future maybe 5 bits per cell and beyond. And what we're seeing over there as well is a set of requirements around low power. A lot of these edge locations are very power constrained. We're seeing requirements around performance with regards to consistency. You have a smaller overall number of storage units, so the ability to spread the load across many units becomes limited, and therefore consistently being able to deliver performance becomes even more critical. We see a lot of dense form factors from EDSFF, E1.L, and so on. And we also see a variety of environmental requirements. Temperatures ranging from -40 to +80 C are really commonplace in the core and in the edge in that case.
So we have covered a vast ground. We started with Moore's law scaling and limitations in compute, disaggregation, and we have gone from the core to the edge architectures. We came back in and we talked about what's happening in the cloud itself with respect to the data architectures, and then we went ahead and talked about the networking part of it with NVMe over fabrics. Pulling all this together is the centrality of data. The proliferation of data and the fact that we are able to store, and storage becomes the big part of the data center. Data center footprint, data center capacity is driven by storage. The capital spending of large cloud data centers is dominated by how much they need to spend on storage. So this is what we call storage at the center of this data revolution. So we got to hear from experts within Western Digital on the centrality of storage, the scaling of flash, how that is enabling this vast amount of data to be stored, the operating systems such as zone storage, the security and the security operations that need to be done to maintain this data, and then all of the evolution in the architectures both at the core and at the edge to accommodate this volume of data. This is an exciting period in storage industry. Western Digital is doing its part to take our moral responsibility to ensure that we are providing you with the solutions that you need to access and create value out of data.